before she moved over to Davis, she held a postdoc at Berkeley. The range of Fran's interdisciplinary research reflects the enormous breadth of the climate issue itself, and in that way is representative of the combined intellectual breadth and depth of a rising generation of young scholars who are in the vanguard of developing the knowledge we need to solve this immense problem. Let me mention two of my favorites among her papers. Your working paper, has it been accepted somewhere yet?
The actual one?
The one on the social cost of carbon.
Oh, no, it's in revision.
Synthesis of evidence yields high social cost of carbon due to structural model variations and uncertainties. This is an area that I love from my experience with the climate models. It's what's hidden, which really matters the most. This paper is now under review and does what few others, if any, other researchers in the integrated assessment domain have dared to do, which is to carefully analyze the assumptions underlying these models, which have a powerful impact, by the way, in the policy arena, and produce the first plausible assessment of the true uncertainty in the social cost of carbon that these models produce, arguably, for our governments. And then the second paper, I urge you to go back and look at, is a 2020 paper, using remarkability to define coastal flooding thresholds, which I particularly like because it uses human perception as measured by social media posts, rather than expert ranking to assess the impact of flood events, and that's a dimension we don't think about often. Today, Fran will describe the long-term, future-looking project of endogenizing climate policy in models that until recently, these models considered anything related to the social concept, except the economic side, from a scenario-based rather than an integrated system perspective. The title of Fran's talk is Understanding Climate Change Implications for Human Welfare, Research and Policy Applications. Please join me in welcoming Fran.
Very much for that introduction and for the kind invitation to be here today. So as was just mentioned, I do have a fairly kind of wide-ranging research agenda, all related to climate change. What I'm going to try and do today is, like, rather than focus on a particular paper, I'm going to try and give you a flavor of kind of a few different strands of that research. And I'm going to try and tie them together, because I see them as really, like, actually quite, like, fully integrated, in the sense that the way I think about the climate problem is a human problem, and it's a people problem. And it kind of, like, people are at the center of our understanding about climate change. And what that means is that, you know, we really need a kind of close and meaningful integration between the climate sciences, engineering, and the social sciences. And that's what a lot of my work is trying to achieve. And I'm going to keep coming back to this diagram to kind of connect the dots and kind of show you kind of where these different studies are fitting in. The broad outline is kind of three different strands I'm going to draw on. One on the welfare costs of climate change, which is very closely related to the social cost of carbon work mentioned in the introduction. One on the kind of perceptions of climate change and climate change risk. And then finally on this question of endogenizing emissions pathways in the coupled climate social system. I'm going to give you a kind of flavor of each. I'm happy to kind of pause and take questions. I'm used to presenting to economists where, like, they kind of batter you with questions on slide 2. But I'm also kind of hoping to leave some time for questions at the end. So the kind of first step here, and I should mention, I'm going to try and also bring in policy applications, because my work is, you know, often motivated by kind of policy applications. I'm kind of trying to give you a sense of where that comes in as well. So quantifying the welfare cost of climate change is really focused on this arrow here, right? We think about the physical changes in the climate system. You know, the reason we care about climate change as a policy problem is because of its effects on welfare-relevant measures that, you know, it kind of don't fall out directly from most climate modeling. With some apologies, I'm going to begin by walking you through a really classical integrated assessment model, the DICE model by Bill Nordhaus, which I know is going to be familiar to some of you, but it's kind of going to be a useful reference point for this work. So what the DICE model does, it begins with a two-factor production model, right, where you have capital and labor that are combined to produce economic output. That economic output is split between investment and consumption in an endogenous savings decision in the model. Investment goes back to replenish a depreciating stock of capital, and consumption is what contributes to welfare in the classic DICE model in a kind of constant relative risk aversion utility function, right? So this is a kind of really kind of standard macroeconomic model right here from kind of like the 1980s, early 1990s. What makes it the DICE model, what makes it a climate model, an integrated assessment model, is that there is an externality from production, right? So production also contributes to greenhouse gas emissions that affect temperature via a simple climate model integrated into the DICE model, and that temperature feeds back to output via a damage function, right? The problem in the DICE model for the social planner, right, is to choose the optimal level of mitigation to maximize the discounted value of the stream of future welfare, right? So this is just like a kind of, this is almost like the simplest representation you can come up with of the climate change problem in a macroeconomic context, which is what the DICE model is really trying to do. If you notice, the temperature, the damage function here, right, falls directly on output. What I'm going to show you here is the significance of that assumption and what happens if you start relaxing it, right? So let me show you kind of why that's an important assumption. Imagine if you have a temperature shock, right? So this is our temperature. It goes up 1 year, and it goes back down. And there are two different worlds, right? There is one world where that temperature affects the level of economic activity, right? And that's an output world, like the DICE framework. And there's another world where that affects the kind of underlying growth rate of the economy. What happens in those two worlds in the year of the temperature shock is identical, but what happens subsequently is really, really different, right? In the output world, you recover to close to your baseline growth path, whereas in the growth effects world, right, your economy is permanently depressed below where it would otherwise be. What that means, right, in a climate change setting is that these effects can accumulate, right? So they add up to really large numbers, right, in a setting where we have these growth rate impacts compared to a setting where you only have effects on the level of economic output. And so this can accumulate up to really large damages if you think that this is one of the ways in which climate change can affect the economy. What are we talking about here, like kind of just mechanistically? Right? Well, growth rate impacts are anything that has a persistent effect on the economy over time. You could think of damages to the capital stock from extremes, disruption due to socioeconomic institutions that sustain economic production, slower technological progress because we have to divert our research and development into responding to climate change damages, and so on. In contrast to kind of a set of levels impact that are often what we think about when we think about climate change damage functions. So lower agricultural output due to heat, right, lower worker productivity, and so on. So in some early work with my collaborator and friend, Delavain Diaz, what we did was we relaxed this assumption in the DICE model, right? So we kind of say, all right, like what happens if we add a second damage function, right, that falls not on output, but on the growth rate of total factor productivity? Right? And not just, we're going to calibrate these two parameters to a pre-existing study done by Del Jones and Olkin using a econometric technique to tease apart these two pathways. What this does, it really changes what the DICE model does, right? So in the blue here is what our two-region DICE model is doing, right? In this model, we split out rich and poor countries to match what the Del Jones and Olkin paper did. And in the red, we're kind of replicating the DICE model in a two-region framework, right? And what you see based on these empirical estimates is the integration of growth effects in poorer regions can add up to really large numbers, right? So without any mitigation, the per capita income in the poorer regions is 40% lower, below what it would otherwise be. But notice that comes from a relatively small effect on average annual growth rate, right? So it's just a cumulated effect that cuts the average annual growth rate from 3.2% in these regions to 2.6. So relatively minor effect, kind of well within the fluctuations of annual growth rates in these economies. What does it mean for optimal climate policy? Well, in the this is now showing you the optimal mitigation pathways within the model, and like I always understand optimal as referring to the model framework, not necessarily anything about real world policy. But within the model, the climate, like the DICE model in red is doing the classic DICE behavior, which is this relatively gradual ramping up of emissions reductions and a kind of transition to net zero by close to the end of the century that leads to a temperature increase of substantially over 3 degrees by 2100. And in our GrowDICE model, right, where we integrate these growth rate effects, right, you see this very, very different behavior of early and stringent mitigation that really zeroes out emissions globally by somewhere between 2030 and 2050. It's really difficult to get the DICE model to do that. you can play around with a lot of other things, but this is a really kind of first order assumption of the DICE model. In some more recent work, kind of led by my PhD student, Bernie Bastian, what we've done is we tried to go to the empirics as well. What we are doing here is, so like coming back to this question of do we have these growth rates, right? They're a kind of first order problem for climate change, but what do we know about whether they exist or not? And in this, we kind of develop a novel statistical technique where we're relying on the fact that temperature varies on a number of timescales, and that lower frequency variation kind of gives us more information about these longer term effects. So effects that are potentially operating through growth rate channels. And this is just an illustration of the kind of time series of temperature in the US kind of filtering out increasingly like the higher frequency variation to give you just this lower frequency variation here. The paper finds kind of, the finding in the paper is certainly consistent with the existence of these growth rate effects. So what you're seeing here are the kind of average estimates split across different countries. If we were only seeing levels effects, right, which is consistent with the DICE model, what you would expect is these estimates to converge to zero very quickly. And instead they stay persistent, which is consistent with a story where you're seeing kind of these longer run impacts to the economy from temperature fluctuations. Okay, changing gears a little bit, this was very much about GDP. It was very much about kind of economic growth and the like market economy. But I want to shift gears a bit too and talk about these other effects of climate change, primarily those that operate through environmental goods and natural capital. And if we think about how climate change might affect the natural systems that we value, we can think of kind of two primary channels here. What economists would call a kind of non-use channel, which is the kind of existence value we place on the existence of species or ecosystems that are going to be driven, kind of potentially eliminated by climate change. And then a kind of set of use values, which are the values we kind of directly derive from the environment, from being able to go and recreate in it, say, or kind of from the like pollution reduction benefits it provides and so on. So climate change impacts on natural systems are big. They're very direct, and they're largely irreversible, right? So when we think of the climate change problem, they really are a big chunk of it. But the cost of these ecological climate damages are very, very sparse, right? And those that exist are incomplete and pretty dated. And it's definitely true to say that they are very poorly, if at all, represented in current estimates of our kind of of the total cost of climate change, right? Which I'll summarize here as the social cost of carbon, right? So come back to this diagram again. How do we start to think about how does the kind of ecological systems, the environment, start to play into a framework like this? And we're going to think about these multiple channels, and we're going to try and layer them into this really kind of abstract, but simple and transparent setting here. So the first thing we do is we split out natural capital in the production function, right? And so this is like, instead of a too good production, we now say economic production depends on three goods, depends on kind of produced capital, labor, and this kind of stock of natural capital, right? Which gives us a new production function that looks like this. So this is a very old debate about is the economy best represented as a two-good or a three-good production function? It is actually quite fundamental to how we understand our welfare as depending on the environment. The reason why is that if you believe only capital and labor appear in this, and natural capital is kind of wrapped up in a generalized capital, natural capital can fall to zero and you can still have plenty of economic production, right? But notice in this representation, if you have zero natural capital, you have zero production, right? So the natural capital is partially, but not fully substitutable with other forms of input into production in this framework. This is an old debate going back to kind of the 70s and 80s and was largely dropped in the kind of initial representations, for example, in things like dice in the 1990s. So that's our use value framework. We then layer in a kind of a welfare value that comes from non-market ecosystem services, right? So the idea that we benefit from the environment in ways that are not well captured by simple measures of economic production, right? And that this is a kind of aggregate environmental good that also depends on these three depends on these three factors. But notice that gamma 2 here is switched with gamma 3, which indicates because gamma 2 is much larger, it indicates a much larger dependence of natural capital in the production here. We also modify the utility function. So don't pay if these functional forms are not familiar to you, don't worry too much about it. But what this is doing, it's saying utility doesn't just depend on consumption of market goods, it also depends on consumption of these non-market ecosystem services, and that these things are imperfectly substitutable with each other. That you can substitute them kind of to an extent, but it becomes increasingly more difficult to do so. And this is based on a kind of small literature, but one going back kind of several decades at this point, that's pointed out that this is really first order importance for the climate change problem, is how does utility depend on the environment. And finally, we add a direct effect from natural capital to welfare that captures the existence value of natural capital. Right? And so this is us just getting direct value from nature, right, from the existence of these things that doesn't operate through any kind of production model. And we again expand utility function to capture that representation. And what we do in the model is we kind of layer in each of those changes and look at how kind of the dice model responds to that increasingly sophisticated representation of the dependence of human welfare on the environment, right? And so what you're seeing here is this measure of the optimal carbon tax, or the social cost of carbon, right? And it goes up from a kind of 2020 kind of dice specification of about $28 per ton, and it kind of keeps jumping as you add in, right, these kind of pathways of how climate change depends on the effects of climate change on natural capital, right, up to a kind of full green dice specification that I think it was about 7 or 8 times kind of the initial dice model. What does it mean for optimal emissions, right? The optimal emissions trajectory really kind of collapses down as those costs of climate change increase, right? And you're kind of ending up with, in the green dice model, kind of a net zero global emissions by about 2050. That has corresponding effects on global temperatures that you would expect. So this is high-level schematic modeling work, right? Very, very abstract. In subsequent work, again led by my PhD student, right, what we tried to do was get a little bit more granular, right? So rather than just having an aggregate damage function, could we draw on what the ecological literature is telling us about climate change impacts on natural systems to try and get a better parameterization of some of these effects, right? And in this, what we're doing is we're really looking specifically at changes in terrestrial vegetation cover, right? And we're going into a regional setting here. Part of the reason we want to go into a regional setting is because we're interested in this question of how do these things play out in a world with unequal distribution of wealth. And what you see in these natural capital accounts, right, is that a much greater share of the wealth of poorer regions, right, which is shown here as the smaller dots, like show up as natural capital, right? So their well-being is kind of much, much more closely related to natural capital than in wealthier countries. And we can draw on this like really like sophisticated modeling that's coming out of these dynamic global vegetation models. And what these do is they're kind of simulating vegetation growth and how that changes in response to a shifting climate. So that's what we are doing here. This is summarizing one of the dynamic global vegetation models that we're using and how things respond to a 2-degree warming, right, around the world. And what you're seeing is you see a shift from forest to grasslands in the tropics, an expansion of forests into boreal areas, declines in total vegetated area in some regions. So this is just like a kind of like decline of vegetation altogether. And in remaining vegetated regions, higher carbon content, right, which is a higher carbon fertilization effect. So what we take this as a starting point, right? These models that are telling us what is the current distribution of terrestrial biomes, right? And how will that change in the future, right? And then we do this tricky step of trying to say for each country, what is the welfare consequences of that shift? And to do that, we use a database of prior studies on ecosystem valuation in different countries and in different biomes to kind of map the World Bank accounting of natural capital to these different biomes within each country. And then we can say, okay, what then is the change in natural capital for each of 50 regions that are included in a regional version of the DICE model that I just showed you. This then maps out trajectories of the welfare effects of natural capital loss across the regions. And this is showing you the kind of, for each region, it's like track in this space of market value change on the y-axis and non-market changes on the x-axis with a population-weighted average shown in the dashed line there. And so some of the interesting things to pull out is that, you know, there's much larger effects on the non-market change. This is a really important welfare metric, welfare cost of climate change that is not going to be captured in standard GDP accounting. And there's also, you can't read it from here, but there is an inequitable distribution in the sense that the poorest 50% of regions are experiencing 90% of the damages, right? So kind of following that like deeper dependence of poorer regions on natural capital. Let me give you tie into some of the policy motivations here. I've brought up the social cost of carbon, right? What that is a kind of a best estimate accounting of the effects of an additional ton of CO2 on kind of the future streams of human welfare. It is an incredibly ambitious, if not foolish thing to attempt to estimate. And yet, why do we do it? We do it because our rules in the US kind of require federal cost-benefit analysis. And you know, if we're going to be doing climate policy in the US, you have to do cost-benefit analysis around it, which means that you need to be able to attach a number to the benefits of emissions reduction. The changes I've shown you to the DICE model that I've kind of worked on previously are structural changes, right? The EPA recently did an important update to our social cost of carbon. It's kind of much improved from where it was. But what it didn't do, it kind of didn't address these kind of structural, fundamental questions about macroeconomic dependence on the climate system and the sources of welfare in the utility function. This is from the paper that Michael mentioned that's kind of currently in revision. And what it's doing is pulling across all studies in the literature and showing you how model structure kind of affects the social cost of carbon. Right? And so in the top, you have this is a representation of the DICE model, right? So versions of the DICE model that are out in the literature. And what I'm pointing out here is the two things I've showed you. I showed you limited substitutability in the utility function and the persistent effect of climate change on growth, right? Both of those, not just in my studies, but in the other ones in the literature too, kind of really show a kind of quite important for shifting that social cost of carbon distribution to the right. We talk a lot about the social cost of carbon, but there are other applications too, right? And the social cost of carbon is not kind of the be-all and end-all of climate change economics. And in particular, this is a report I was involved in while I was working at CEA, And we were responding to an executive order that said you have to integrate climate risks into federal budgeting, right? And one of the things the federal government does when it produces its budget, it has to project economic growth out for 10 years in the main budget and for 25 years in the long-term budget, right? But if we think climate change is going to have an effect on economic production, right, then you might want to think like, well, maybe that's something that we should start bringing in, right? And what this exercise was, it was an exercise in essentially doing exactly that, where kind of looking out over 25 years, like what is the US debt to GDP ratio under these different emission scenarios, right? And how does that compare to a scenario where you don't integrate climate change at all, right? And like because of the slower economic growth from climate change, right, essentially your tax revenues kind of don't increase as much as they would otherwise, and it bumps your debt to GDP ratio up a kind of modest amount, well, at least modest compared to like the like unsustainable trajectory that we're on otherwise. So that's one application. And finally, I want to mention this, an application around natural capital accounting. And so kind of in January of 2023, the Biden administration released this really important 15-year strategy for developing a set of economic environmental statistics that will, ultimately enable us to bring in like these non-market effects that are not well captured in GDP, that we've known since the creation of GDP were not well captured in GDP, but we've never kind of actually done the formal federal work necessary to create a set of alternate statistics. And so this work is gonna gradually be changing that. Okay, and onto my kind of strand 2, and this is kind of related to this part of the diagram around understanding and perception of climate change risk, right? And I think this is really important because what it's doing, how people or institutions or firms, whatever you're interested in, how they understand climate risk is going to then shape like the responses that we're interested in, whether those are mitigation responses or whether those are adaptation responses. And to set this up, I want to kind of describe how I see this problem, right? So I see fundamentally climate change, understanding climate change as an inference problem, right? And what do I mean by that, right? There's this great quote, right? Climate is what you expect, weather is what you get, right? If I'm going to like rephrase that slightly, I can say climate is a probability distribution, right? And weather is a realization from that distribution, right? And if you think of things that way, right, what's weird is that no one sees climate. Climate is a statistical distribution, and what we get to see from it is simply the realizations of weather. I have a little asterisk here. That asterisk is a reminder for me to mention that we do have modeling frameworks, right? And so models like catastrophe models or like general circulation models, what they can do is they can give you a flavor of that statistical distribution, right? But I'm going to set that aside for the moment. That's all, we can talk about that in discussion if you want. And so the questions I'm interested in here is kind of given this setup, how might people and firms, how do they do this inference, essentially? And what are some of the implications of that then for, communicating climate change or for responding to climate change? In the introduction, Michael mentioned some of my work using Twitter data. I'll mention a different paper here, which is a kind of slightly earlier paper where we were using Twitter data to really try and measure how people infer, like how people are surprised by the weather, right? This is an apocryphal, maybe potentially Mark Twain quote that everybody talks about the weather, but nobody does anything about it. We're kind of interested in using the fact that everyone talks about the weather, maybe to explain why nobody does anything about it. And so what we do here is we kind of take the corpus of weather-related tweets in the continental US, right? And what we are able to do with that then is we're able to say, literally, what type of weather is remarkable in different places at different times, right? Because we are measuring people remarking on the weather, right? And what that does, under certain models, right, that remarkability allows you then to infer how people's expectations are changing, right? Because people kind of tend to remark on things that they are either that are highly surprising or that are quite consequential, or both. And so we pair this measure with the temperatures, both immediate temperatures and a time series of historical temperatures, to understand how people react to changing climate conditions over time. What lets us kind of pull out this effect is the fact that climate trends across the US are highly variable, right? So these kind of decadal trends, although on average everywhere is warming, right? Different places are warming at different rates at different times of year. And what that means is that how unusual this temperature is for your location for a particular time of year, right, depends on that particular history. And that variation is kind of what we're going to be able to use to tease apart, like, how remarkable is a temperature anomaly if you had it this year, but if you also had it last year and you also had it the year before. So this is kind of main results here. And what you're seeing, right, you're seeing the estimated response to a temperature anomaly, right, both in the current period and given experience of that same temperature anomaly in different numbers of years prior, right? And this is the cumulative effect. So what is my probability of changing my tweeting behavior, right, given that I get a temperature anomaly in this time period, and then if I also had it in the previous period and the previous period and the previous period and so on. So what you see is that there is this instantaneous effect. What I'm showing you here is a kind of particular set of cold, right? So this is like kind of cold regions and months. And so people tweet when it's really unusually cold for that time of year because it's kind of miserable, right? And they're less likely to tweet about it being hot, right? But the thing to notice is that that effect declines. And that effect declines on about a 5 to 8 year period, so that if you kind of have that consistently unusual temperature for between 5 and 8 years, you kind of don't remark on it anymore. It ceases to become remarkable. We can take that into an inference model. So we can kind of say, okay, assuming that this is how people understand temperature anomalies, what does that mean for the perception of climate change? So this is pulling out US kind of continental temperatures under like very high emissions. This is RCP 8.5 into the future. What the squiggles are showing you, they're showing you individual realizations of the climate model. And then the solid line is showing you the average across all the ensemble members. And you see very large absolute warming over the 21st century. But if we think people are kind of pretty quickly updating their idea of what normal temperatures look like, then this is what it might actually feel like to people experiencing those temperature anomalies. That they're certainly positive on average, but the magnitude is much smaller. And notice, given internal climate variability, you also get negative temperature anomalies, right? So this is like, wow, it's like snowing, in places where it like used to snow all the time, right? What that means, what that actually means for climate change, and work on climate change, the communication of climate change, that's not what we address in this paper, but this is just kind of pointing out that this normalization effect could be quite important. Let me turn now to kind of some more recent work that is kind of taking this fundamental problem of climate change inference, right, and translating it into a policy setting that I became pretty interested in while I was working at the Council of Economic Advisors. And so this is like, I'm sure you have seen a lot of this reporting about, if not experienced firsthand, challenges in the US property insurance market. So let me just give you that motivation up front. There's been rapidly growing insurance premiums and increasing areas where kind of coverage is unavailable at any price in some areas in the last kind of 5 to 10 years. A primary indicator of challenges here is these public last resort programs. So these are programs that states put into place to provide coverage for homeowners that are just no private insurer is kind of willing to offer them coverage. These are explicitly intended to be last resort plans. They're financially set up that way to operate that way. But in Florida, Louisiana, and California, the value underwritten by these plans has more than quadrupled in the last 5 years, right? this should be alarming, like just by itself. In California in particular, the financial model is incredibly unstable. There's been financial deterioration of private insurers offering coverage. This has been documented in Florida, whereas there is some publicly available information. 50% of value underwritten by private insurers in Florida comes from insurers that are unable to obtain a credit rating by the standard credit rating agencies. Right? 9 insurers have gone bankrupt in the last 3 years in Florida. Right? This is not a kind of healthy financial situation. And there is substantial evidence that these challenges are related to growing losses from natural disasters in the insurance industry and the kind of growing cost of like transferring that risk from the primary insurer to global reinsurers. This is a graphic from some nice reporting in the New York Times that just shows kind of profits and losses for the last 10 years across a few states in the US. This is a subset. This is the worst subset I'm showing you. But what you're seeing is like, this is not just a Florida problem, right? There's kind of a lot of different states are showing up here. And it's also true that on a national average basis, insurers have lost more money than they've gained on property insurance in the last 10 years. This is not a kind of stable situation to be in. So I'm going to use that as a motivation to kind of come into this inference question, right? And what I'm thinking about the insurer's problem of estimating the climate distribution, right? Why do I want to know that as an insurer? Because that tells me the probability of a loss on any given policy, right? But like I said, no one observes the climate, right? Instead, like I'm faced with an inference problem. And in this setting, I'm looking at the problem of flooding in New York City. So what this is the daily maximum rainfall in New York City at the Central Park rain gauge. And it's showing you like the maximum for each year, right? So imagine that this is going to be a very simple illustration, but imagine that my losses depend on what this like annual maximum rainfall is. My problem as insurer is that I need to use that historical information to say, okay, what is that climate distribution? What is that probability distribution of these outcomes? Because that is going to determine my expected losses on any given policy, right? And I'm going to put us in a Bayesian setting, right, when the insurer is going to look back at the study a climate record, right, and they're going to do their inference using the historical weather record to come up with that probability distribution. I'm going to show you 2 different updating processes. One, maybe this is a setting 10 years ago when we can say, climate change, sure, it's a problem, but that's like a 50-year problem, right? Like, sure, it's going to be bad, but I'm writing a policy for this year, and basically I'm pretty safe saying that the last 30 years are a pretty good representation of risks this year. And I'll call that assumed stationarity in the sense that I'm able to assume the climate is stationary over this period. And then what I do, I kind of enter with a prior over a kind of parameter of my distribution. I use all the data, right, to update that prior, and that gives me a posterior distribution over this parameter for 2024. So that's the first updating model. In the second, all I do is I say, well, maybe that's not true. Maybe there is actually some underlying trend in the climate distribution, right? And actually, my inference model should allow for a trend. This is super simple, right? It's just a linear trend from an initial starting value, right? But I kind of allow for a gradual trend, and then my inference is going to be over the 2024 value of that parameter, right? That comes from the joint posterior distribution over these 2 parameters. If that's a mouthful, I apologize for those not familiar with Bayesian updating. But essentially, all I'm doing is I'm saying, like, what happens if I relax this assumption, right? What happens if I relax this assumption and I allow for the possibility of climate change? I don't say, even though we know it's probably true that climate change is exacerbating extreme rainfall, right? The prior I have here is centered at 0, right? So it's saying, like, I don't know, it could be going up, it could be going down, but I just, like, it might be changing, right? And what I do in this paper is I essentially, like, simulate that, and I simulate this change in updating through insurance market parameters, right? So what this is showing you for this parameter, which for those that care about it is scale parameter of a Weibull distribution. It's a fairly conservative assumption about the updating process. This is showing you just that effect of shifting the inference model. And what it does, it pulls that posterior distribution out to the right. The reason why that has to be the case is that you have exactly the same amount of information, right? You have the historic result record, but because now you're trying to fit 2 parameters instead of 1, you've effectively lost information, right? And so this different inference process, by definition, has to have a broader kind of result in a kind of more uncertainty about the climate distribution that you face. So this is showing you the posterior of the scale parameter. What I'm going to do is I'm going to pull, and what you see is like these are showing you the 95th percentiles. So I'm going to show you what the rainfall distribution looks like at that extreme level, right? So this is what it looks like. So this is like a kind of 95th percentile of the rainfall distribution. You know, it's shifted. You know, it's not dramatically shifted, right? But notice what happens in the tails, right? The probability of an event of 5 inches or more kind of increases modestly, right, from 20% to 31%. The probability of an event of 8 inches or more than triples. It's still pretty low, right? But it's tripled. It's more than tripled. Why is that a problem for insurer? It's a problem for insurers because our losses are nonlinear in the hazard, right? And so this is a damage function that is based on NFIP claims in New York City. It's rough. There's no fancy econometrics here, but it's giving you an illustration of how this propagates through impact, right? So because the damage function is very nonlinear, very bad floods are much, much, much worse than kind of smaller floods, right? What it does, it exacerbates this kind of change in the tails, right? And it leads to, in the simulations, kind of what I show, is that just this shift in the inference kind of produces much higher and more variable insurance premiums, right? Because the insurers kind of, you know, their expected losses have shifted to the distribution of expected losses shifts dramatically to the right. It results in higher costs of risk transfer, because reinsurers are also doing this updating process. That cost of risk transfer, like the insurers are going to want to pass that on to the policyholder. It raises the cost of supplying the insurance, and you get a higher risk of bankruptcy, right? So you're paying all this additional money, but you still have higher financial instability in the insurance market. Climate change is a gradual process, right? But these effects can arise suddenly, right? These are shocks because the shock is coming from the updating process. That can happen overnight. And it's also systemic, right? This is a systemic loss of information in the historic weather record that cannot be addressed by the standard insurance tool, which is diversification, right? Like insurers are already diversified, but they've kind of, everywhere they are becoming more uncertain about the climate, right? There's kind of nowhere you can go to deal with that. And so these are related purely to the ambiguity, right? This is not about, you know, like losses from flooding going up or down. It is purely the ambiguity cost of climate change. They're additional to actual climate impacts, and so far are kind of largely unquantified, I would say, within our estimates of climate change costs. Okay, in the last few minutes before we kind of move to questions, let me show you my kind of final thread of research. That Michael also alluded to in the introduction. And what this is doing, this is getting at kind of this part of the diagram, right? And what I'm kind of trying to get at here is the kind of observation that human influence on the climate system is really the primary determinant of where the climate system is going to go over the 21st century. And yet, in essentially all our modeling, it appears as exogenous, right? It kind of either we put emissions pathways into our climate models, right? Or we kind of put constraints on our energy models that say, you know, meet this policy, kind of meet this temperature target. But if we want to really understand the Earth system, right? Humans are like, you know, the key part of the Earth system and how it's going to evolve over the next 100 years and into the future, right? And so a kind of one policy motivation, so I would say that's a kind of scientific motivation. It's really trying to get at this observation that humans are like, you know, a key part of the Earth system that have been, you know, by and large kind of treated as outside of it in some of our modeling work. there's also a policy motivation, which is where is our climate future going to take us, right? Kind of 10 to 15 years ago, this really kind of scary, very scary range by 2100 with a distinct possibility. We now have current policies and kind of near-term commitments that really bring down that upper range. And kind of if implemented, and that's a big question, right? If implemented, but these longer-term net zero pledges would come within shouting distance of meeting the Paris Agreement, right? So this question of where is policy going is really first order in understanding what climate change is going to look like over the 21st century. So why don't we do it? Well, there's a very good reason, and that it's really, really hard. And I think people quite sensibly have said, maybe we won't try and deal with that. And what I've done is I've kind of expanded my diagram here to kind of illustrate just how many disciplines and how many insights are important in understanding this effect. I think that these different levels are kind of often treated very separately across the social science disciplines, right? And yet they kind of interact in this setting in important ways. So what my co-authors and I did in this paper was we really tried to do what is admittedly very much a first pass, right? But it's essentially trying to put that all together, right? And kind of comb the literature for documented feedback loops that connect these different elements, use as much data as we can find to then try and constrain the model, and essentially use it both to look at the future, but also to understand the system, understand where we might see tipping points and under what kind of parameter combinations. So it has, yeah. So what we do here, we develop this model, and then we partially constrain it, so we're able to run it in a probabilistic manner, using an admittedly very thin set of observational constraints. Public opinion, climate policy, and emissions over a short historical period. And then we essentially simulate it in a Monte Carlo mode, so we kind of run it forward under these kind of partially constrained parameter sets. And then we use clustering analysis to pull together the resulting emissions pathways into kind of storylines that are kind of familiar to people that have worked with emissions, but what these do, they arise endogenously from the model, rather than kind of coming exogenously. So this is our set of runs. The width of the bar is giving you the fraction of our runs that fall into that pathway. Our model is tippy. It's a little maybe by construction. And what it does, it sees a high likelihood of accelerating climate policy over the next few decades. A large majority of model runs kind of result in temperatures between 2 and 3 degrees. And we can pull out, what I think is neat about this setting is we can pull out what parameters are really important in driving variation in the emissions. One thing that's interesting is this is emissions projections that come from counting up the nationally determined contributions. This is from a completely different study, but they fall kind of well within our range, and our emissions are not constrained at all by what policy commitments countries have made. I'll just mention that this is an important application. Why do we need to do this? Really important application is that we need to be taking action on adaptation. To take action on adaptation, we need to be able to provide probabilistic emission, temperature and impact forecasts. This is a paper that showed incorporating these constrained emission scenarios and constrained climate sensitivity can substantially reduce the uncertainty in climate change impact relevant variables. So I'll just kind of conclude there, make sure we have some time for questions. I think people are essential here, and they're essential because their values and priorities kind of are what determine what makes climate change a problem. People are going to be the ones kind of responding to climate change, taking actions to reduce risks either through mitigation or through adaptation. And I will leave it there. So thank you, and any questions?
You're happy to take your own question?
Yeah, happy to. Yes, I'm sure there was a fire hose. Yes.
As you know, in the big climate
Thank you.
My also work on similar
Yeah.
topics, but most of our approach is really looking at technology risk,
Yeah.
system model,
Yeah.
integrated system model. So this is a very selfish question. I wonder if you can talk a little bit more about what do you see as the type of human actions or institutional questions that are best suited for stylized modeling, such as size and dice, and what do you see as limitations of using stylized models so that maybe some of the other modeling approaches can potentially tackle those remaining human questions?
Yeah, I think that's a really good question. And I really like, I think you have a paper kind of pointing out that, our technical details in modeling is very different across different frameworks. And it's very, and this was a problem we dealt with in the work I mentioned on integrating climate risks into the forecast. That some of these macroeconomic models that are used for these projections are very, very simple and kind of, quite stylized. And we had, people with like fancy GCAM, right? And they're saying like, okay, where do we plug in our like energy capital stock? And it's like, ooh. And so I always think of, I think of models as solving problems, right? And like, why do you want to do modeling? It's because you have a question, right? And that, depending on what the question is, that's going to lead you to different solutions. Like, in this setting, the reason it's really different from the paper I presented at the end, very different from DICE, because we're not doing any optimization, right? We're saying there's no social planner doing, we're just in a different question space, right? And because of that, that allows us to integrate all these feedbacks that if you're in an optimization setting would kind of blow up your problem. And I think that's just what we're interested in here. I think the question of how you could speak more to the technology system models, we do a very abstract, as you might have read, a very abstract representation of these kind of technology feedbacks. I always think of it as here's the parameter. This parameter is trying to capture something that is coming from these much richer, engineering-based models, right? Does that move you into maybe an emulator setting? I think there's a lot of scope there, but I kind of agree, I think, with some of your writing that, the scale of, the degree of detail should be related to, the whole of what you're trying to do. And that's going to mean stepping away from highly technical optimization models to some degree, but you're trying to, you definitely don't want to lose the insights that those are bringing. Yeah. Okay, I apologize.
I'm just curious. I want to make sure I'm not misunderstanding. Climate change is not factored into the current economic systems we have for judging the market. And to what extent, in total layman terms, is that not factored in?
Yeah, honestly, that's actually a really good question. And that was something that came up a lot when we were thinking about this integrating climate risks into the forecast, right? Because a lot of these forecasts, what they're doing is kind of statistical in nature. And if you're looking at something like prices, particularly asset prices for long-lived things, if the investor is anticipating climate change, then you kind of already have a little bit of climate change in your forecast. And I think that's a bit of what's going on in the insurance market, right? That investors, financial markets are not magic, right? They're made up of people. And these people interact under certain information states. And if you're looking at that in the insurance setting, well, maybe what you had a whole bunch of people kind of realizing, oh, we know climate change is coming, but maybe climate change is here. And maybe we need to go back and revisit our historical weather record and really update our understanding of what current risks are. And that's going to have this ripple effect through the insurance market. And so it's not a trivial question, I think, because people know climate change is happening, right? And increasingly it's becoming certainly more discussed in financial and economic settings, in which case you'd expect for people to be anticipating it and trying to integrate it into their decision making. Yeah. Yeah.
Yeah, thank you. It's really fantastic work, so thank you for that.
Thank you.
I have two questions. One is related to the role of inequalities and the micro scale.
Yeah. Yeah.
climate change rather than just on aggregate numbers such as with HGDP
Yeah.
or global natural capital.
Yeah.
The second is about the work you alluded to with the agents at different scales that
Yeah.
all matter for climate mitigation.
Yeah.
And do you have some work that tries to relate, let's say, the top-down and bottom-up causes of social change and how those two sides of it might interact? So might have feedback between policy recommendations and maybe collective action at the bottom-up level.
Yeah, so on the first question about kind of like I would maybe, could I characterize it as like within region inequality, like not like cross-country, but like, you know, you have income inequality within a country. Yeah, so actually I have a couple students like starting like some work on that, and there's been some work previously using versions of DICE that disaggregate regional inequality. And essentially what we're going to do is we're going to try and interact that with our green DICE model. And I think what we're thinking about here are settings where utility of different income groups depends differently on the environmental good. So what that could capture is things like subsistence economies. And that, you know, that has, my intuition is that that would be quite important. It would certainly be important if there's any kind of inequality aversion from the decision maker. And so like that, we're gonna start exploring that piece of it. On the, your second question was about bottom up and top down. So I mean, I think what I presented here is very global scale. I do tend to gravitate to that because of the like thinking of climate change as a global problem. But then if you look at like, you know, the literature that's going to get at these individual questions, the questions of how do people take action related to social networks and social norms, like I would say I'm a kind of active consumer of a lot of that research, and I kind of tend to like ask how is that going to aggregate. And you know, you know, I'm familiar with, I haven't used myself agent-based modeling, but that's like, you know, is potentially kind of one way to get at that. Or, you know, I certainly could think of that as like parameterizing like the more like system dynamics type models that I showed. I think we have time for one more, yeah.
So I'm in solar energy myself, so I maybe have two questions. Maybe answer only one.
Sure.
The first question would be, so with all your economic insight, when a policymaker comes to you, what would you suggest or what on good energy policy? And the second one is to which extent you incorporate the risk of climate tipping points. So when you're across a certain threshold, you get some abrupt changes that are irreversible, but maybe then also have kind of a chunk.
Yeah, so on the first question, I mean, I am like, I would say like at least half an economist at this point, so I'm at least half required to say like if policymaker came to me, I would have to say carbon pricing. It is a first best great policy. You can solve the distributional like problems, you know, however you want. You can use the revenue for a whole bunch of great things. It's just a good policy. And you don't, you know, you can ramp it up over time. You could exempt US retail gasoline. Like there's a lot of like ways you could play with it that I think, you know, the subsidy kind of forward like policy we're in now is important. It's important for technical, kind of driving technical progress. But the kind of carbon price on top of that is just gonna complement that in really valuable ways. That's gonna like just push everyone in the right direction and not like lead to unintended consequences. And then on the second question was on, oh yeah. I personally haven't done work on that, but if you, this work we did looking at the kind of totality of social cost of carbon research, it has been like addressed by other papers to a certain extent. So you see there's these like two categories here, climate tipping points and damage tipping points. And so there's kind of a number of papers that have like tried to integrate those kind of irreversible like jumps in various ways. And they are important, and you know, they kind of interact with some of these things in important ways. Yeah. Okay. Thanks everyone. Yeah, thanks for the great questions.